All right, today we're going to crack open the digital toolkit that powers, well, pretty much every piece of software you use. We're talking about data structures and algorithms.
You know that feeling, right? Your favorite game just snaps on, loads instantly, but then another app, it just sits there and spins and spins. It's super frustrating, but what's actually going on behind the screen?
And look, it's easy to think, oh, I just need a faster computer or a new phone, and yeah, that could help. But the real secret? It's in the smart choices programmers make long before they even start coding. It's all about designing for efficiency right from the get-go.
So let's actually do that. Let's open up this digital toolkit. Inside, you're going to find two key things: the containers that actually hold all the information, and the recipes that tell the computer what to do with it.
First up, let's talk about organization. How do you store and arrange data so you can find exactly what you need right when you need it? This is where data structures come into play. A data structure isn't just a random pile of information. No way. It's a carefully designed system. Think of them as the shelving, the filing cabinets of the digital world. You have to have the right system in place, or everything else falls apart. Okay, to make this a little more real, let's look at 3 of the most common containers you'll find in any programmer's toolbox. Each one has its own special strengths and weaknesses. First, we've got the array. The best analogy for this is an egg carton. Seriously, each slot has a number, an index, so you can go straight to slot number 5 and grab that egg instantly. It's incredibly fast for getting to stuff. The catch? The size is fixed. If you have a 12-egg carton, you can't just shove a 13th egg in there. Next up is the linked list, and this shows a totally different trade-off. Picture a train. It's really easy to add or remove a car from the middle, right? You just uncouple and recouple the links. That flexibility is its superpower. The downside? If you need to get to the 50th car, you have to walk through the first 49 to get there. You can't just teleport. And our third container is the hash table, which is basically a magic dictionary or your phone's contact list. You don't flip through every single page to find a name. You use a key, the person's name, and you jump instantly to their number. This makes finding, adding, and removing data ridiculously fast. Okay, so we've got our containers. We know how to store our data. But what do we actually do with it? That brings us to the second part of our toolkit, the plan, also known as algorithms. An algorithm is really just a step-by-step recipe. That's it. Your data structures are the ingredients, all neatly organized. The algorithm is the set of instructions that turns those ingredients into a finished dish, whether that's sorting a playlist or finding the fastest route on a map. And what's really interesting is that there's no single perfect recipe. Take these 2 approaches. The greedy method is kind of impulsive. It makes the best possible choice right now without really thinking about the future. Then you have divide and conquer, which is more strategic. It takes a huge problem, breaks it into bite-sized pieces, solves each one, and then stitches the answers back together. So with all these different containers and recipes, how do you choose the best one? How do you measure performance before you've built the whole thing? Well, for that, you need a spec sheet. And that spec sheet is called Big O notation. It's really just a way to talk about how an algorithm's performance changes as the amount of data gets bigger and bigger. It answers the one question that really matters. Will this stay fast if I go from 100 users to 10 million users? And if you look at this chart, you can see exactly what I mean. O log n is the dream. Performance barely changes as you add more data. On is solid. It scales just how you'd expect. But on squared? Quadratic. That's where you get into trouble. That performance curve gets steep, fast. An algorithm that's totally fine for 100 items might take forever with 10,000. And this isn't just theory. This chart shows the real-world difference. The faster sorting algorithms, like quicksort, run with that very good on log n complexity. You compare that to the slower ones like selection sort at on squared. Well, on large datasets, that's the difference between an app that works and one that's just frustrating. So this brings us right to the core of what a programmer does: understanding the problem and choosing the absolute right tool from the kit. And here's the crucial thing to remember. There is almost never a single best answer. It is always a game of trade-offs. Do you need lightning-fast access and you can live with a fixed size? Use an array. Do you need the flexibility to add and remove items easily and you're okay sacrificing some search speed? A linked list might be your answer. I love this quote I saw on a developer forum because it just cuts right through the noise. It's a simple, powerful mental checklist. If the sequence of items is critical, start thinking about a list. If you need to find things instantly by a key, a hash table should be your go-to. So, why does any of this matter? Because these fundamental choices, these tools from the kit, they aren't some abstract computer science concept. They are the invisible architecture of our entire digital world. Think about it. When Google Maps finds the fastest route and avoids traffic, that's a powerful graph algorithm at work. Your social media feed, mapping out that huge web of friends and connections, also a graph. Even that simple undo button you use all the time, that's a stack, a structure built on the simple idea of last in, first out. And the list just goes on and on. Autocomplete suggestions in your search bar, that's a tree structure. Your computer juggling multiple tasks, it's managed by queues. That lightning-fast search in a massive database, powered by B trees. They're everywhere. Every single feature is powered by a specific tool chosen for that specific job. So the takeaway is this: software that feels effortless, that feels intuitive, that feels like magic, it isn't magic at all. It's the result of deep thought, careful planning, and the elegant application of the right tools from this fundamental toolkit. And that leaves us with a final question for you to think about. Now that you've peeked inside the toolkit, what other parts of your digital life, from your streaming service to your online shopping cart, do you think are built on these same simple yet incredibly powerful ideas? Thanks for watching.